Hello everyone, my name is Hongbo Chen. I'm a PhD student from Indiana University. I'm presenting our work on verifying confidential computing as a service framework today. First, let's start with an example. Have you ever experienced spilling out coffee? Have you ever worried about cleaning overnight coffee cups? Do you want a cup which never spills out coffee and never bother cleaning? Definitely yes. This is also the problem our confidential computing community are trying hard to solve. Enclaves provide a trusted execution environment to hold users' private data, just like coffee in the cup. We don't want to see privacy leakage while executing and privacy left over after the execution. Similar concepts can also be found in privacy regulations like GDPR. TE claims 3 security primitives. First, attestation. It guarantees the identity of the enclave code to the end user, ensuring that the only expected code can be executed. Second, isolation. It prevents outside attacker from stealing secrets. And third, encryption, which protects the confidentiality of the data. Now, let's see how the story changes when confidential computing becomes a service. A third-party developer first submits task code to the service. We call it confidential computing task or CC task. The data provider then negotiates a key after attestation with the service. After that, she feeds the input data, and the platform starts to execute an workflow of data decryption, task execution, and result encryption. Finally, the output is returned to the user. For example, the user can send genomic data to the service, and the task can conduct analysis. This situation changes a bit when there are multiple data providers. The service can start over a new iteration right after the last one, or even serve data providers concurrently. For a data provider, the task is not trusted and verified. She trusts the service, but verify it. She doesn't trust other users' input. However, TE still cannot achieve comprehensive protection to private data. Attestation cannot prove the code is indeed trustworthy. TE's isolation ignores internal threats, which may also lead to active data leakage. Furthermore, potentially incomplete data encryption and cleaning can result in privacy left over, which might be stolen by other users. Therefore, simply using TE does not guarantee no data leakage and secret withholding. Our goal is to prove to the user that the enclave service cannot threaten their private information in those ways. We propose proof of being forgotten, a principle that regulates the code dealing with secret. It has 2 requirements, no leakage and no residue. No leakage regulates that all secret and secret tainted values are within a confined area during the computation. And no residue requires that after the computation, no secret is found inside the enclave. Well, these requirements are intuitive, proving that to the end user can be challenging. To model the behavior of enclave and enclave programs, we first build a formal model. Because of the time limitation, we currently skip the details. But note here, we introduce a new concept, zone. The basic idea is to confine all the sensitive data inside this zone. Based on this model, we can prove 2 theorems. First, for procedure, we can see if its initial state is secure, all memory writes are within the zone, and it aborts when error occurs, then the execution does not leak secret. And on the other hand, we also need a no residue theorem. We define the zero-rise procedure, which clears the values stored in the confined zone. And we see that if the zero-rise procedure is executed at the end of a function, then no sensitive data residue is left inside the enclave. And those 2 theorems are mechanically checked by Cog according to the abstract model. Next, we embark on the realization of the PoBF-compliant enclave service under the guidance of those 2 theorems. Before we start, our design goals are: privacy leakage is statically detected for enclaves. Secret residue is zeroized for all functions. And PoBF compliance is verifiable and testable. We also expect minimal modifications for the CC task is required for the third-party developers, and different hardware Ts are supported. Here is an overview of our system. Our artifacts include a T-agnostic library, T-specific enclaves, and a verifier executed at the user end. Also, here is a CC task submitted by third-party developer, which is not trusted. We call the whole system PoBF-compliant Framework, or PoCF. Let's start with the pillar of PoCF. We know that the type safety derives memory safety, and those two collaboratively build control flow integrity. But what about the workflow integrity of the CCaaS? It's guaranteed by the PoCF library. We build a state machine for the CCaaS workflow using type state in Rust. The state transitions of the task, data, and key are specified, and these transitions are enforced by Rust. And the specification is verified by Prusty here, and all the checks are static. Finally, the workflow integrity is guaranteed with minor runtime cost. Therefore, backed by Rust and Prusty, PoCF library obtains workflow integrity. Such guarantee is platform agnostic. Then, let me talk about how we achieve no residue. We modify the heap allocator to zeroize the objects on heap when it's released. And second, we allow no mutable global variables. And third, we introduce instrumentation as a function epilogue to deal with the stack and register. Remember the zeroize procedure appeared earlier is executed at the end of functions, and thus PoCF achieves no residue. Another requirement of PoBF is no leakage. We verify the edge function calls does not leak secret. For example, OCall in SGX and call to the hypervisor in SEV. We use static tint analysis. Tracking of key is done through type state, and tracking of the data needs help from a separate tint analyzer called Mirai for untrusted CC task code. Thus, PoCF achieves no leakage. Last, let's talk about how the end user can conduct verification. The code of PoCF is publicly available. When the third-party developer submits CC task, the developer runs the verifier on the CC task with PoCF. If the verification passes, the PoCF enclave is compiled with the CC task. Data providers can obtain the source code and conduct verification at their end before feeding data to the remote enclave service. They can calculate the enclave measurement by rebuilding the enclave, and they finally feed the private data after remote attestation. These steps can also be performed by a trusted builder to protect the proprietary code, and thus PoCF can be verifiable. Here is our evaluation results. I'm not diving into the details for now, but just highlight some key results. PoCF reaches the design goal and incurs negligible runtime overhead in CPU-bound tasks. However, because of lack of I/O optimizations, we observe performance degradation in I/O-bound tasks. And also, the data flow tracking tool has some accuracy concerns. We publish our code on GitHub, and you are welcome to play with that. Okay, any questions?